Welcome to Theory of Computation. This is lecture number 45. Today is the last lecture of this course. So rather than covering another topic or seeing a proof of another theorem, what we would do today is just reflect on what we have learned. So we will go through the contents of the course, we would go through what we have learned and see how it has made us wiser, how it has given us ideas, how it has helped us understand problems that we could not understand without taking this course on computability and complexity. Computability and complexity are the foundations of computer science. We are trying to ask extremely basic questions, extremely basic philosophical questions, and we would like to find answers for these questions in very precise sense. And therefore, what we do is we resort to the language of mathematics. We state our results and ideas as mathematical definitions, and then we prove these things as theorems. So every claim made in this course actually comes with a bona fide proof. We have not hand-waved over anything. We have proved each and every single claim that we made in this course. And that's the defining thing in theoretical computer science. It is an exact science. We are not saying things which may be true, but we are exactly and precisely saying things which we can prove are true. So let's go over the course contents and let's discuss briefly what the ideas are and what we have learned in this course. So today we will discuss what we have learned in this course and go over the major results and accomplishments of computability and complexity theory. The most important achievement of computability theory is the formal definition of an algorithm. See, algorithms is an extremely old subject. However, people were designing algorithms when they actually did not have a definition of an algorithm. Euclid was designing algorithms. Algorithms are thousands of years old. Perhaps the first algorithms were designed by people in caves. However, these people could not pinpoint what the definition of an algorithm was. Even Euclid called Euclid's algorithms was just a precise, exact procedure for computing the GCD. The definition of a general algorithm was not known to us for a very long time. Even when Hilbert, in his famous 1900 speech, gave his 10th problem, which in modern day language asks if Diophantine equations can be solved by an algorithm, or can an algorithm find solutions to Diophantine equations, or tell us if a given Diophantine equation has a solution or not. He did not define what he meant by an algorithm. He said a finite procedure. So, an exact and finite procedure, but he did not give us the definition of an algorithm. One of the major accomplishments of computability theory is that it gives us a precise, mathematically precise definition of what an algorithm is. And this is done via the Church-Turing thesis. Let's review what the Church-Turing thesis is. The Church-Turing thesis asserts that the intuitive notion of algorithms is captured by the mathematically precise notion of a Turing machine. This allows us to formally talk about algorithms and prove things about computations and algorithms. So the Church-Turing thesis says that the precise definition of what an algorithm is given by a Turing machine. So if somebody says, I want you to design an algorithm, well, they are telling you to design a Turing machine. The precise mathematical thing that they're asking is for a Turing machine. Algorithms is an intuitive notion, and it becomes mathematically precise when we talk about Turing machines. That's an abstract mathematical object. Once you have precise definitions, then you can definitively say things about the structure that you're talking about, which in this case is algorithms. So for example, if I did not have a precise definition of what graphs are, I can never do graph theory. Graphs are very simple objects and it's very easy to define them. On the other hand, algorithms are not very simple. In fact, Turing machines, when you think about it, seem to have this clumsy definition, this clumsy kind of look. When you read the precise mathematical definition, it seems to be a long-winded, complicated definition, but that's what it takes to define what an algorithm is. Once you have the precise mathematical definition, now you can talk about algorithms in a mathematically precise way. Thus, the Church-Turing thesis is a huge step in computer science. It tells us the precise definition of the most important notion in computer science, namely algorithms. Another extremely important theorem that we proved in computability theory was the existence of a universal Turing machine. And this is a theorem of Turing, who says that there exists a universal Turing machine such that when you give this universal Turing machine a description of another machine and an input, this machine behaves like if you were running the machine whose description is given on the input. A major part of this proof is the realization that we can encode the description of a Turing machine into a string. Another important idea was the fact that we can make a Turing machine simulate another Turing machine by only reading its description. So there are two major ideas in this theorem. The first idea is the existence of a universal Turing machine. And that's very central in computer science. What this says is, if you think about the universal Turing machine as your PC, then what it says is that you only need to make one universal Turing machine. And now if you want that Turing machine to behave like some other Turing machine, all you have to do is provide that description to it. And this is what all the software is based on. You have software, you have an operating system that reads other programs and runs them. And that's the basic idea of a Turing machine. But one very important ingredient that goes in this proof is the idea that Turing machines can be encoded by strings. They can be encoded by 0-1 strings. This idea may seem trivial to you because you're computer science students. For you, every input is eventually encoded as a file. Every input that you give to a computer eventually is given in the binary language. So it seems trivial to you that graphs, matrices, formulas, programs and everything eventually, when you write it down on a hard drive, becomes a 0-1 sequence. So encodings seem very natural to you. But the reason is because you have thought about it for such a long time. And you have thought about computer science for such a long time. You would imagine that the whole map of the world can be encoded as a 0-1 sequence and be put on a hard drive of a computer. But this idea, when it first came out, was not very clear. It required an intellectual jump. In fact, one of the major achievements of Kurt Gödel who proved Gödel's theorem before Turing proved his theorem, was to actually realize that mathematical statements could be represented by numbers. And this today to us seems a triviality. You write down a mathematical statement, say, you type it out in a Word file, and then you save the Word file and you get a 0-1 sequence, and that can be the encoding of that mathematical formula. But this was a huge intellectual jump for Kurt Gödel. Similarly, for Turing, it was a huge intellectual jump to actually think of the idea that machines can actually try to analyze descriptions of other machines. That seems like circular reasoning, but it's not. What you can do is you can describe a machine as a 0-1 sequence, and now you can think of the machine that's reading that sequence as analyzing the description of another Turing machine. So the existence of a universal Turing machine and the idea of encodings is very central, very basic, and it is not difficult. things do not have to be difficult to be fundamental. But these concepts are extremely fundamental, and once people realize these perhaps simple things, once people realize that, then huge progress can be made because you have the foundations laid out right for you. Then we said that we will make a definition. We called a language decidable if there existed a Turing machine, so that it halts on all inputs and accepts the strings which are precisely in the language. So it must reject all strings which are not in the language, since it has to halt on all inputs. This gives us a precise definition of the notion of algorithms. We realize that the language accepted by Turing machine, by the universal Turing machine, does not seem to be decidable. So Turing gave us the idea of the universal Turing machine, and the universal Turing machine takes another Turing machine, description of another Turing machine and a string, and starts behaving like as if you were running that machine on that given string. Now if that particular machine did not halt on that particular string, then the universal Turing machine would not halt on this pair. Therefore, the straightforward simulation that shows the existence of the Turing machine does not show that the language recognized by the universal Turing machine is decidable, or whether that problem, the decidability or the acceptance problem for Turing machines, can be solved by an algorithm. An algorithm is a Turing machine that halts on all inputs. So what we did was we defined these two very interesting languages. These are very, very interesting and very closely related problems. The first was what I call the acceptance problem for Turing machines. It's the set of all pairs m, x such that m accepts x. And a closely related problem, which I call the halting problem, is AH, which is the set of all pairs m, x such that m halts on x. These two languages are very closely related. You can take a few minutes to show that if one of them is decidable, then the other one must be also. And that is not a hard exercise, and you can do that in 5 or 10 minutes after taking this course. So studying one problem is like studying the other problem, and this is more famously called the halting problem for Turing machines. So what we note is ATM, the acceptance problem for the Turing machine, is the language accepted by the universal Turing machine. However, the universal Turing machine is not a decider. Thus, the natural question that arises is this language decidable? So we want to ask if we can make a universal Turing machine that would halt on all inputs. That would be an amazing practical machine that you would have. You would write an operating system which will run your program, and if your program was going to go into an infinite loop, the operating system will somehow tell you that your program is not going to ever end. That's the task that is being given to us. So can this problem be solved by an algorithm? Can we make a decider for the halting problem? And here we proved an amazingly interesting theorem of Turing. This theorem says that this language ATM is not decidable. The amazing thing about this theorem is that it points out to us something which probably would not have crossed our minds. The fact that a well-defined computational question can be undecidable. When most people think of algorithms or programming, they tend to have something in the back of their mind, which is that if somebody were to give them a computationally well-defined problem, they should be able to write a program that solves that problem. Of course, many programmers will tell you that they can probably write very complicated programs, and sometimes they take a lot of time. But the fact that no program can be written to solve a well-defined computational question is something that does not cross everybody's mind. No one can actually just sit down and think of bizarre problems that they start believing for some reason or the other can't be solved by a computer. However, Turing did precisely that. Not only he thought of the idea that all computational problems, all well-defined computational problems may not be computable, he actually found one and showed it to us that it is not computable. He proved that the halting problem was an uncomputable problem, that no decider can be made for this problem. This points out to us the one possibility that would not have crossed our minds. That's why it's such a huge intellectual jump. Pointing out of this problem allowed us to break a mental barrier. And now what we do is we can start thinking about whether other computational problems are unsolvable or uncomputable. If we did not have Turing's theorem, perhaps we would not think of other problems. Based on this theorem, the undecidability of the halting problem, we were able to prove that several other problems are undecidable. A generic result called Rice's theorem stated that all non-trivial semantic properties of Turing machines are undecidable. The Rice's theorem is a very beautiful theorem. You can interpret it in many ways. Now, here we have to be very careful. Remember that computability theory and complexity theory are exact mathematical sciences. So we make precise definitions and we prove precise theorems. And when you define things precisely, well, they may or may not have interpretations that you want to give them, intuitive interpretations that you want to give them. But intuitively, Rice's theorem is somehow pointing out the inability of Turing machines to analyze other Turing machines. In some sense, it's saying that the ability of Turing machines to analyze other Turing machines is very limited. Nothing that is semantic can be analyzed by a Turing machine. So syntactical things may be analyzable by Turing machines, but semantic things are not. So that gives us limits on the computational power of Turing machines. Here, I would like to stop and just remind you that Turing machines is accepted to be the only practical model of computation around. There is the Church-Turing thesis, which in one sense says that the intuitive notion of algorithms is captured by the mathematically precise definition of a Turing machine, but not only that, that if something is computable by a computational device, then it's computable by a Turing machine. That Turing machines is the universal model of computation and the only one. If you think about it in that way, then Rice's theorem and the undecidability of halting problem are huge things. They are saying that there are certain problems that you cannot decide mechanically. Then we looked at a very natural question that was undecidable. This problem seemed to be a puzzle, but turned out to be undecidable. That was the post-correspondence problem. Thus, problems which naturally pop up can also be undecidable. So we saw an example of a puzzle which one would want to solve using a computer, but it turns out that you can never write a program to solve the post-correspondence problem. Now, these results have huge implications. This would mean that if somebody were to hire someone and say, write a program that would solve the post-correspondence problem for me, well, that person should say that they work better from home and start looking for another job, because they're never going to find an algorithm. There isn't one. And if your boss is not smart enough to understand these proofs, then that would be the best option for you. After that, we started with a very small puzzle, a curiosity. So we asked a very interesting and a simple question, which was, can you write a program which does not access any input device, and when you run this program, it prints out its own description? Is it possible to write a program that when you run will print out its own description? And this puzzle was a very curious puzzle, and you can give it to your friends who have not taken a course like this and see how they fumble over this puzzle. It's a beautiful little problem. When we tried to solve this problem, we realized that one could write such a program, And we were able to answer this question in the affirmative, and not only that, we were able to come up with a technique which told us that a program can have access to its own description. This statement was formalized in the recursion theorem. So the recursion theorem is a statement which says that programs can have access to their own descriptions, and therefore you could write programs that analyze themselves and then make a decision. However, the analysis power of programs is severely limited. So there was some sort of a circular reasoning, and in fact, if you looked at the program that prints itself, there's a very clever way of coming out of this circular reasoning. The original proof of undecidability of halting problem was based on diagonalization. The recursion theorem gave us another way of proving undecidability results. One could easily prove Turing's theorem using the recursion theorem, and many other problems which we know are undecidable, you could prove them that they were undecidable using the recursion theorem. We also proved some fixed point theorem using the recursion theorem. So recursion theorem is a huge tool that you can use in computability theory to prove that things are undecidable. After that, we also looked at problems that arise from mathematical logic. Mathematical logic is one of the most important branches of mathematics. In mathematical logic, we study what is a proof, what is an axiom, what is a statement, how we do mathematics, and what constitutes of a well-defined structure, and how do we write down mathematical statements, how do we analyze them. It's one of the foundational branches of mathematics. What we did was we specially studied two kinds of things in mathematical logic. We started studying mathematical logic and started studying logical theories. One of the theories was Presburger arithmetic. Presburger arithmetic is made by taking statements over the quantifiers for all and they exist, taking integers as the set of all as our universe, and then writing down statements using the usual Boolean connectives and the addition operator. Multiplication is not allowed in Presburger arithmetic. We realize that this kind of arithmetic, the theory that we get out of it, is decidable. You could write an algorithm which would decide whether a statement in Presburger arithmetic was true or not. So we showed a very non-trivial algorithm that Presburger arithmetic is decidable. However, Presburger arithmetic is not the most interesting arithmetic in the world, because most mathematical statements that we write down require multiplication. For example, you can write down Goldbach's conjecture or other interesting mathematical problems, but you have to use multiplication. You cannot write them down in Presburger arithmetic. So our main interest in mathematics is looking at what we call the piano arithmetic. And what we did was we showed one of the greatest results that was proved in mathematics in the last century, namely Gödel's incompleteness theorem, which says that piano arithmetic is, there are statements in piano arithmetic which are true, but they are not provable. So the fact that piano arithmetic has statements which are true and not provable also told us that statements in piano arithmetic are undecidable. This was a shocking and wonderful result. After that, we moved to another topic which we studied in computability theory, and that was called descriptive or Kolmogorov complexity. The goal of Kolmogorov complexity was to define what does it mean for us to have information, to come up with some formal definition of information. This gave us a fundamental definition. Kolmogorov complexity actually defines what does it mean for a string to contain a lot of information. Kolmogorov complexity says that a string has a lot of information if it is uncompressible. If you cannot compress the string, then there must be a lot of information in the string. We proved several theorems in Kolmogorov complexity. We defined incompressible strings. We furthermore showed that most strings are incompressible, that there are a lot of incompressible strings. And that was done via a very simple counting argument. Then we saw that Kolmogorov complexity does have many of the properties that would be required if you were to define the amount of information in a given string. Lastly, we showed that any property that holds for almost all strings must be false for finitely many strings that are incompressible. So, if you have a property that holds for almost all strings, then it cannot be false for infinitely many incompressible strings. In that sense, we showed that incompressible strings, say finitely many, are indistinguishable from a computational point of view. Thus, incompressible strings look random from the point of view of any computable property. And this was the main result that we proved in Kolmogorov or descriptive complexity. After that, we went to a different kind of a subject that we studied. It was called complexity theory. So now our goals were much more practical. Let's discuss what we learned in complexity theory. Then we changed our focus and started studying complexity theory. This now we were talking about problems that are solvable in practice. Thus we study computable problems and ask what resources are required to solve these problems. See, computability theory was actually studied before electronic computers were built, before there were any serious computing devices. And there the question is whether a thing is computable or not. A thing is computable if there is a procedure, finite procedure, or an algorithm that will solve the problem. But what if that algorithm took extremely a long time, or what if it required huge amount of space? Then the problem cannot be solved by any computer as an electronic computer that you could buy. So now, once electronic computers and digital computers came about, it was much more exciting to study problems which could be solved practically. Now, we do not want to just say that this problem is solvable in principle. We want to say that this problem is solvable in practice. And therefore, complexity theory was developed. Complexity theory actually was studying how many resources are required for us to solve a given problem. And the two resources which are most important is, one is time and the other is space. And so complexity theory studies how much time is required to solve a computational problem and how much space is required to solve a computational problem. Of course, these are not the only two resources, but these are the most important resources. So we started studying complexity theory. This was questions which, if we answer, will have, in some sense, practical implications. What we did was we precisely defined space and time complexity. We also noted that k-tape Turing machines can be simulated by one-tape Turing machine with quadratic blow-up in time. Thus, all models of computation are not equivalent if you are strictly talking about how much time does it take to solve a given problem. But if you were willing to give up, say, polynomial, say if you were willing to afford a quadratic blow-up, then in some sense complexity theory is also a universal theory. So there is a universal model of computation, and you can think of the amount of resources required by these Turing machines to be the amount of time or the space that would be required by your program. And the answers that you would get will not be exact matches, but they would be within a polynomial of what your program could do, or how much your resources your program would require. We defined non-deterministic and deterministic time and space complexity. This led us to two naturally defined classes. The first class that we called P and the second class that we called NP. P is the set of all problems that can be solved in polynomial time, and it is widely accepted that if a problem can be shown to be in this class, then it can be solved in practice. This is, of course, just a mathematical definition, and it doesn't need to completely correspond to what happens in practice. It is conceivable that there are computational questions which require polynomial time, but the degrees of this polynomial, the upper bound on the running time, is so high that the algorithm is actually not practical. However, what has happened is historically this class P was actually defined implicitly by Jack Edmonds, who said that a good algorithm is one that takes polynomial time. Historically, that definition has turned out to be very good. It seems to capture the notion of what we can solve in practice or not. The other class, NP, is just a non-deterministic version of this class P, and what we want to do is we want to study what happens if we allow non-determinism. Why is this class NP so interesting? Well, one of the reasons is that because it contains a lot of interesting problems that we want to solve in practice. It contains a huge number of problems that seem to arise, that seem to pop up everywhere. The class P captures the problems that can be solved in practice. However, the class NP contains a lot of practical problems that we would like to ask. So we simply ask a very interesting question, and that question is, are these two classes equal or not? So the central question, the P versus NP question, is the most celebrated open questions in computer science. It is considered to be a deep question whose resolution will enhance our understanding of computation in a very fundamental way. This is one of the most celebrated problems actually in all of theoretical sciences, and it's considered to be a very, very deep question. The Clay Mathematical Society has declared it as the problem of the millennium. So that is a huge distinction for a problem. The Clay Mathematical Society only declared 7 problems which they thought were one of the most important problems, the deep questions in mathematics, and of course they put some monetary award on these problems also. And the P versus NP question was one of these problems. Why is it that this problem is so celebrated or so considered so important? That's because if you think about P as the class of problems that we can solve practically, NP seems to be a class of problems that is just a little bit bigger. NP contains a lot of problems that we can realistically wish to solve in practical time. So the question whether all those problems that we can realistically wish to solve in practical time, whether we can solve them in practical time or not, is an extremely important and exciting question. Another reason I think that the P versus NP question is so celebrated is because we have no idea how to prove it. We have not seen any serious attacks or dents which have been made in this direction in computer science. No serious progress has been made on this problem. What that means is the P versus NP question actually is showing us that there is something fundamental that we do not understand about computation. There is some fundamental thing that we have not gotten our hands on, and therefore we can't seem to make any progress towards this problem. That's why anyone who solves this problem will have to be extremely creative and come up with beautiful ideas that will enhance the fundamental understanding that we do not have right now. The study of the class P and NP has led to the theory of NP-completeness. When we prove a problem is NP-complete, we show that if it can be solved in polynomial time, then all problems in NP can be solved in polynomial time. Thus, it provides us with hard evidence that a problem is hard. However, it does not provide us with a proof, at least not till the P versus NP question is open. So, one attempt to understand the P versus NP question was via NP-completeness. And the theory of NP-completeness developed a lot, because when people were able to show that a problem is NP-complete, that gave humongous evidence that the problem is computationally hard to solve. One of the most spectacular theorem in this area was the Cook-Levin theorem. The Cook-Levin theorem states that satisfiability is NP-complete. Well, what does it mean that satisfiability is NP-complete? Let's recall that satisfiability was a concrete computational question. It was a language. It is just one language, whereas the class NP is a class of infinitely many languages. When we said that satisfiability was NP-complete, that meant that every problem in this class NP, every language in this class NP, was reducible to one problem, namely satisfiability, which also happened to be inside this class. Thus, this problem seemed to have the whole complexity of a whole class. Rather than having just complexity of one problem, it somehow is so complicated that if you solve it, you solve every problem in the class NP. This theorem can be read in two ways. The first way to read it is that if P is equal to NP, if and only if SAT is in P. The second way to read it is to say that SAT captures the complexity class NP. If you think about it, the first statement, P is equal to NP, if and only if SAT is in P, seems to say that if you want to prove that P is equal to NP, it says, then all you have to do is give a polynomial time algorithm for this one problem, satisfiability. Another way to think about this is SAT is the best candidate if you want to show that it's not in the class P, because if there is any problem which is not in the class P, then it must be SAT. SAT must be one of them. So, since many computer scientists believe that P is not equal to NP, therefore, this gives us a lot of evidence that satisfiability is a difficult question. After that, using the Cook-Levin theorem, we were able to prove several other problems are NP-complete. These problems came from different branches of computer science. Some of them were graph-theoretic questions like independent set, colorings, vertex cover. Subset sum was a problem from arithmetic. We had satisfiability, which is a problem from logic. And this showed us that NP-complete is a rich class of problems. So, the set of problems which is NP-complete is a very diverse class of problems. And all these problems are actually translations of one another. They're just written in different language. You can take a satisfiability question and by looking at it, very quickly write down a question in graph theory, say about independent sets, and it'll be equivalent. If this formula was satisfiable, this given graph will have an independent size of some size. And to go from one to the other, it would not take you very long. So this class NP was a very diverse and rich class of problems, and we showed that several problems are NP-complete. Similarly, we then started studying determinism and non-determinism from a space complexity point of view. The class P space and NP space were defined. So we defined two classes. One was P space, another was NP space. And they were just the space analogs of P and NP. And we used similar kind of ideas. We asked similar questions that we asked about P and NP, about this class P space and NP space. The class P space captures problems that can be solved in reasonable space. The class NP space was a natural non-deterministic analog of the class P space. We again asked if these two classes are equal. So once again we asked a very interesting question, whether you could remove non-determinism at polynomial cost. Or in other words, is it true that non-determinism gives you extra power when you look at things from a space complexity point of view, from a polynomial space complexity point of view? Well, there was a pleasant little surprise, a theorem of Savage, which showed that P space is actually equal to NP space. So, although P versus NP question is still unresolved, the P space versus NP space problem has been solved. P space is equal to NP space, and this was Savage's theorem. Savage's theorem was just a very clever algorithm which is very space efficient, and of course it solved one particular problem. It solved the reachability problem, and then using the reachability problem we showed how every problem in P space, NP space could be solved in polynomial space. That was a very clever idea needed to do this theorem. The study of P and P space led us to the theory of P space completeness. Once we realized that P space is equal to NP space, that question was set aside, and now we compared P space with the class P, and we developed the theory of P space completeness. So we asked the question, is it true that all the problems that can be solved in polynomial space, can they also be solved in polynomial time? That is comparing the class P space with the class P. So that led us to the theory of P space completeness. When we prove that a problem is P space complete, we show that if it can be solved in polynomial time, then all problems in P space can be solved in polynomial time. Thus, once again, it provides us hard evidence that the problem is difficult. However, once again, it does not provide us with a proof, because the P versus P space question is still open. So this led us to the theory of P space complete problems. P space complete problems by definition are NP hard, and the reason is because NP is contained in P space. And in this case, what we did was we were able to prove an analog of the Cook-Levin theorem. We were able to find one problem that was P space complete. Namely, we showed that TQBF is P space complete. After that, we asked the question that we know a bit about the Cook-Levin theorem, and we know what kind of problems we expect to be NP complete. Somehow, after looking at several NP complete problems, you get a feeling for what kind of problems will be NP complete. So we asked ourselves if we could pinpoint what does it make a problem P space complete, or can we build a big repertoire of problems which were P space complete, which would, by looking at them, we could develop our intuition further. Well, we then proved two problems are P space complete. These problems came from what we call combinatorial games, or two-player perfect information games. One of the games was a formula game, which was just a restatement of quantified Boolean formulas. The second one was very interesting. It was called generalized geography. And then we commented that several combinatorial games or two-player perfect information games are known to be P space complete. So if you want, you can go on the internet and find out some very interesting results and read very nice papers which prove that many precisely defined versions of popular games are P space complete. In the last part of the course, we studied the class L and NL. These were space complexity classes where the space requirement was logarithmic, and once again we proved that one particular problem called path was NL complete. However, this time we used a different reducibility, namely log space reducibility. Well, the reason for using log space reducibility was that the class L and NL are already inside P. And now what we want to do is we want to compare L with NL. So polynomial time reducibilities take too many resources. we want to bound the resources even further. So we allowed our reducibilities to use only logarithmic space. And we were able to show that NL, the problem path, is NL complete with respect to logarithmic reducibility, log space reducibility. This would mean that if path were in L, then NL will be equal to L. So that's the status of L versus NL is in some sense slightly the same as what is the status of the P versus NP question. We also notice that Savage's technique does not yield a result about L and NL. However, the big surprise was the last theorem that we proved was that NL is equal to co-NL. This gave us an example of a non-deterministic complexity class that is closed under complementation. So far, we had not seen any complexity class, any non-deterministic complexity class which was closed under complementation. We did see NP space, but NP space was just, by Savage's theorem, was just a reformulation of P space. And therefore, since P space is closed under complementation, NP space also would be closed under complementation. But here is an unresolved question. We do not know whether L is equal to NL. And yet we can prove that NL is equal to co-NL. And this was a very pleasant, complicated proof which showed that a non-deterministic space complexity class was closed under complementation. This is where we ended our last lecture. Now, the question is, at the end of this course, we can ask ourselves, what more to study? What have we missed? Theory of computation is a very vast field. It's a very huge subject. No one can teach one course and even cover a small fraction of what is known or all the interesting results that are known in complexity and computability theory. To do that, it would require a lifetime. It's a very active field. So you can ask yourself that after finishing this course, what can you study more? What kind of results would be interesting to look at which come from complexity theory? So what I'm going to do is point out some directions which I think are interesting. Let me explain to you that what we have done here is done of our first course in computability and complexity. So the emphasis has been on foundations. I wanted to present to you foundations, not the most current results. Current results in computability and complexity are very exciting and they are also complicated, but you must have the foundations in order to understand those difficult results and their proofs. So what I'll do is I'll give you some suggestions of what you can study further if you want to study more complexity theory. Theory of computation, there are many exciting things in it, and you can look at these in the future. These include randomized complexity classes. We have hardly talked about randomization. Randomization is an amazing resource. I hope you have seen some randomized algorithms, and you probably would have seen how having access to random bits or how making random choices can help us perform computations fast. So randomized complexity classes and their study is a wonderful area which is very active, and there are many open problems in it. There is another subject called the polynomial time hierarchy. The polynomial time hierarchy is actually a hierarchy which starts from the P and it is contained in P space, and it's a hierarchy, it's an infinite hierarchy of problems, and there are many interesting problems which are complete at various levels of this hierarchy. So imagine somebody cutting up P space up into infinitely many pieces and then looking at each piece and asking interesting questions about it. It's a very nice subject, and you can further look into that. There is an exciting thing which is called the hardness of approximation. So remember that algorithms, if we think about from a practical point of view, are not the only way to solve problems practically. Randomized algorithms is a more general notion. We can allow computers to make random choices. But not only that, we are also willing to settle for approximate solutions. Suppose you want to find the cheapest tour from in a graph. Well, you would, if that problem is NP complete and takes exponential time to solve, you'd be happy if somebody were to find cheap enough tour for you. We did look at approximation algorithm in our course. However, there's exciting results in hardness of approximations, and this all is due to one very beautiful theorem called the PCP theorem. Not the post correspondence problem, this is called probabilistically checkable proofs, and that theorem was one of the biggest achievements in computer science in the 1990s. So that's a topic that you can study, and it's a very active subject now. There are other topics that you can study in quantum computation and quantum complexity. You can look at cryptography, and this list goes on. Well, we have run out of time in our last lecture, but I hope you'd continue your study of complexity theory and computability theory. So, good luck to you. Thank you again for taking this course. Goodbye.